So today I'm going to start something kind of new and maybe with a slower pace is to discuss this new point of view of symmetry. So basically, the key player here is so-called categorical symmetry. So I need to explain what is categorical symmetry. The motivation is really that we have many different symmetries. We don't know the different symmetry can give rise to different phase and phase transition. Certainly, phase and phase transition depend on symmetry. Similarly, we have anomalous symmetry. Anomalous symmetry also do the similar thing. This can give rise to different phase and phase transition. And the higher symmetry, anomalous higher symmetry, and all that. And including this so-called non-invertible symmetry. And the higher version of this non-invertible symmetry. And so because we have so many different kind of symmetry, so there's a desire that we have some kind of a unified theory to describe all these symmetries together in the same fashion. So that's one motivation for the to develop this theory for categorical symmetry. And so then, what is a categorical symmetry? Then it's actually there's many point of view, and one point of view is that this categorical symmetry is a gravitational anomaly, so it's kind of anomaly. We also know that anomaly can constrain the low energy dynamics, just like symmetry can constrain low energy dynamics. So it turns out that this so especially this non-invertible gravitational anomaly is something very general. It turns out it happened to be the symmetry we want to talk about, this categorical symmetry. Then another point of view is simpler to understand. It's really symmetry plus is a dual symmetry. We view symmetry, dual symmetry together at equal footing. And this combination of symmetry and dual symmetry is a categorical symmetry. So actually, I'm going to present this picture first, because this may be more familiar to kinetic people. Basically, the symmetries, we have symmetry charge, we have this symmetry transformation, and we have this order parameter, order operator, things like that. The dual symmetry actually like a distorted operator. It's actually we are pretty familiar with. It's talking about the defect. So basically, thinking symmetry, dual symmetry together is like thinking order parameter, disorder parameter together at the equal footing. So it's one way to do this combined picture. Okay. It turns out this combination of symmetry, dual symmetry together can also be viewed as a topological order in one higher dimension. So this combination corresponds to a topological order in one higher dimension. This led to this holographic picture. And this is not surprising, actually. It's really because if you think categorical symmetry as a gravitational anomaly, then anomaly and topological in one higher dimension is related. So therefore it's pretty natural from the anomalies point of view. Okay. Then the more precise definition of topological in one higher dimension would be like a so-called non-degenerate braid diffusion higher category, something scary. But we discussed a little bit about this, how these anions, braidings, those data form so-called category theory. So this basically is kind of a more precise mathematical description of a topological order in one higher dimension. The point is that this kind of combination of symmetry, dual symmetry, when you combine them together, we no longer can use a group theory or even higher group theory to describe them. So we need a new mathematical formulation. This new mathematical formulation happened to be this non-degenerate braid diffusion higher category. So that describes this symmetry. The difference is that usually when using group theory to describe symmetry, we don't care about dimension. The symmetry in every dimension described the same group. And here is different. And even the so-called same symmetry in different dimensions are described by different categorical theory. So this categorical symmetry depend on dimension a lot, very sensitive to dimension, and in higher dimension, the theory can be very complicated. Okay, and once you have this formulation, this generalized formulation to describe this categorical symmetry or this generalized symmetry, Then you can using this mathematical framework to study the symmetry breaking states, topological order, SPT, SET, all these states together in this framework. So there's a holographic picture to understand all those states and give this some kind of classification, which basically is this paper. And but all this so far this looks like a kind of up in the air, you know. So actually, there's even more concrete way to describe or even derive this is using some kind of algebra point of view. And so I'm also going to discuss this because what is the symmetry? The symmetry is really just a selection of a symmetrical local symmetric algebra. Because we usually view symmetry as a transformation. The symmetry is a transformation, but actually in quantum physics, symmetry is not about transformation. Symmetry is about a subset of operator we call local symmetric operator. And this local symmetric operator gave rise to allowed Hamiltonian, allowed the perturbation, allowed the measurement, and their correlation function correspond to experiments. And so it's really this algebra of a local symmetric operator. So later we will show that this from the algebra of a local symmetric operator, we can obtain a subset of a so-called algebra of a transparent patch operator. And this algebra somehow is using that you can derive this braid fusion category. And so therefore there's a operator algebra point of view of this categorical symmetry. So basically what I'm trying to say is that if you give me a algebra of symmetric local operator, then you can derive this braid diffusion category, and you can derive what is a categorical symmetry. So there's a more concrete way to do so. Yeah. Okay. So then one may ask why you care? You know, why you develop such complicated theory for symmetry. The main thing is that it is necessary because although in a mathematical system we usually only encounter zero form symmetry, but however at the low energy we may have an emergent symmetry, and the emergent symmetry can be very general, and so those emergent symmetry control low energy dynamics. So that's why we do need to consider or care about those very generalized all this kind of generalized symmetry. And so maybe near the end of this lecture series, we'll go here to give some example to see how the emergent symmetry and the gapless states determine each other. Here, the gapless states we call the gapless liquid states. We mentioned a little bit in the first lecture. Naively, you can say that it's a gapless state, but with a linear dispersion relation. So, but we don't view Fermi liquid as a linear dispersion relation because there's transverse direction. The energy do not depend on the momentum. Here, the energy really becomes zero at a single point of momentum, and the energy increases linearly with the momentum. So those are kind of we feel that this kind of gapless liquid states maybe is easier. So probably we can use a symmetry to determine them. So that is a hope why we consider all this symmetry. And so the idea is that to understand these gapless liquid states, the first we have to have a label for them. It's very similar to the situation when we first encounter fractional quantum Hall states. When we first encounter fractional quantum Hall states, we say it's a quantum liquid. But at that time, quantum liquid means we don't know. We don't know what's in it, and it's just a mess. Okay. And now with entanglement, we start to feel that, the quantum liquid is like a crystal, have a lot of internal structure, which can be characterized by entanglement or anions, fractional statistics, and etc. And so nowadays we say that this quantum Hall state or topological order can be characterized by this modular tensor category, or even higher braid fusion higher category. So we have a label for that. So same thing is that like for the gapless liquid state, to have a systematic understanding of a gapless liquid state, we may first try to say, can we find a good label? And it's not just like a phase A, phase B, you know, some good label. And so here we're kind of proposing that maybe the emergent symmetry can be a good label for gapless liquid. And then we even try to push it further, kind of try to maybe dream or conjecture that maybe emergent symmetry is a complete label. So if that's true, that'd be amazing, because then we just need to tell the symmetry of a gapless liquid state. Then from symmetry we can compute all the physical properties. So this basically is kind of program we try to push that when the emergent symmetry is so general, maybe it can be used a label to completely label gapless states, and then from emergent symmetry we can derive other property. So that means one can develop a theory for gapless liquid states based on emergent symmetry, and so then from there you can compute many other properties. So this is just another motivation why we want to study this generalized symmetry. Okay. Yeah. So let's imagine if this is this is indeed doable. Suppose we can indeed using this emergent symmetry to develop a general theory for gapless states. Then we need to really have some questions. So what is a theory for describing the generalized symmetry? Then we just say that maybe topological order in one higher dimension. And then why topological order in one higher dimension can determine gapless states? And that connection actually is about boundary relation. So basically the symmetry determine gapless dynamics, just like topological order determine the dynamics of boundary. So these two relations may be similar. So therefore to develop a theory for topological order and its gapless boundary is like to determine the relation between symmetry and the gaplessness, a gapless property. Okay. So let's just so that basically is kind of general picture. So eventually we will study the topological order and the gapless boundary, and this study is kind of like study how symmetry determine low energy property. So it's kind of using this kind of picture. So now let's just go to some very concrete examples. So what is a categorical symmetry? What is symmetry? What is dual symmetry, and etc. Yeah. But do you have any questions for this kind of general picture? So let's just give a very simple example. What is a symmetry? What is dual symmetry, and how they combine into a categorical symmetry? So the simple model is considered one plus dimension transverse field Ising model. So we have this spin live on the side. Then this ZZ coupling, just a spin ferromagnetic coupling. And then we have a transverse field in X direction. Okay. And so in this case, we know that there's a spin flip up and to down. It's a spin flip is a Z2 symmetry because the Z changing sign, X don't change sign, so 2Z also do not change sign. That's it. Okay, so this is a way to describe symmetry using transformation. So here we want to do a shift. We do not want to use a transformation to describe symmetry, but we want to use a conservation law to describe symmetry. But conservation law more like a fusion, as we discussed in the last lecture. So it's we want to use a fusion ring to describe symmetry. And for Z2 symmetry, how I do the fusion? I think it's pretty obvious, but let me just go slowly. So exactly what is logic? So this symmetry transformation select so-called local symmetric operator, which can be ZZ or single X. There's a more local symmetric operator, but they can be generated by these two operators, we believe. Okay. So actually, this local symmetric operator is like an experimental instrument or the allowed operation. And so this local symmetric define the allowed operation. Okay. And then because this allowed operation have some constraint, so they have some limited capacity. They cannot do certain things. Okay. So what they cannot do is correspond to conservation law. For example, you can choose the basis, kind of left-right basis. So we can ignore the Hamiltonian, we just choose the left-right basis. And choose a reference state that all spin pointing to the right is my reference. Then from here, we can see that this left spin point to the left will have a mode to conservation. But this mode to conservation is respect to this local symmetric operator. So we can apply this local symmetric operator to this configuration. We find that this ZZ can flip a 2 spin, but cannot flip a 1 spin. And X do not do anything. So therefore, this the single right-left spin cannot be destroyed by this local symmetric operator. So actually, in categorical language, this local symmetric operator is called morphism, and this left spin is called object. So the morphism act on the object, so it's kind of categorical language. But let's not worry about that. Okay. So we can describe in this kind of conservation using more familiar fusion ring language. That is using this 1 represent the ground state, means nothing or trivial excitation. And the E describe the single left spin. This motor conservation can be viewed as a fusion ring. This EE became 1. So this is what we discussed last week. So this kind of fusion ring really describe the conservation law and describe symmetry. So therefore we can using, so this is the picture we'll adapt to use this to describe the symmetry. Okay. And also we can see that this IC model have a 2 phase. One is a Z2 symmetric phase when H is very big. And we have the Z2 spontaneous symmetry breaking state when H is small and there's a critic point. And using the symmetry, using the Z2 symmetry, we can see that the both critic point and the Z2 symmetric phase have a symmetry. But the Z2 spontaneous breaking state, this ground state don't have symmetry. So we have this kind of picture. Okay, so that is pretty standard picture of the Z2 symmetry, but I described in a way which is easy for me to see a hidden symmetry. So if you follow that line of thinking using local symmetry operator and this to find their capacity and to find the fusion rule or conservation law, actually you can also find a dual Z2 symmetry. In this dual Z2 symmetry, we choose a different basis. We choose up and down basis. Okay. Then we have up and down basis. Then we have a domain walls. You can see domain wall in a different basis. You can see domain walls. And then this domain wall also have the Z2 conservation, because again you can use this ZZ operator. Here the ZZ operator do not do anything, but the single X operator flip a spin, either create a 2 domain wall or moving 1 domain wall around. Okay. So therefore, the domain will also have a Z2 operation. So if using the M to describe domain wall, and using 1 to describe ground state, here it is tricky. To be more precise, I should use a 1 to describe this symmetrized ground state. This superposition is also a ground state. And so this is more precise. Using 1 to describe this symmetrized ground state. And the M describes domain wall, then we also have this M times M equal 1. So this is a fusion. Okay, so this is Z2 dual symmetry. And in terms of Z2 dual symmetry, we have a different picture. That is, in the symmetry breaking states, that's where this domain wall costs energy. So in the traditional symmetry breaking state, the ground state just all up plus all down. Whenever you create a domain wall, it's cost energy. So in this phase, we better not have a domain. They do not like a domain wall. So this without domain wall, so domain wall do not have condensation. So this actually is symmetric phase for this domain wall charge, or maybe for the dual symmetry. So this is the symmetric phase for dual symmetry. Okay. Then in the originally the symmetric phase of original symmetry can be viewed as the domain wall energy getting lower and lower, and eventually the domain wall condense and drive this phase transition. And then we get this symmetric part. Okay. So therefore, the phase diagram became that in original symmetry breaking state, we have is a dual symmetric, but the original symmetric state is a dual simultaneous symmetry breaking. And here you already see something very interesting. The critical point actually also have a dual symmetry. So critical point have both a symmetry and a dual symmetry, although the two gapped phase only have one of a symmetry or dual symmetry. So this kind of very interesting feature, which we are going to explore later. Okay, so really the point is that the categorical symmetry is really symmetry plus dual symmetry. So from this point of view. So in some sense, we say that we have symmetry charge that's more familiar with. We have a symmetry domain wall, like symmetry flux. We also view them as some kind of a charge of a dual symmetry. Then both symmetry are conserved. And we try to say maybe this putting these two symmetries together is reasonable because the critical point have both symmetries. And actually the critical point have a strong fluctuation of both a symmetry charge and a dual symmetry charge. So both symmetry are effective. And actually, this is the main motivation why you want to put two symmetries together. Because then we say, yeah, maybe if you only use Z2 symmetry to look at the critical point, maybe that just has a partial. If you take both symmetry, we may get a new understanding of critical point. We may get some making some progress because we combine two symmetries together. Okay. So therefore, this categorical symmetry is basically putting symmetry and dual symmetry together and treat them as equal footing. And to the degree we don't even try to call which one symmetry, which one dual symmetry, just they all kind of all together something. And this kind of thing together is called a categorical symmetry. And it's okay, it's actually kind of a little bit strange. So we will later try to explore this. But the one point I want to say that although we have two conservations, so this is one conservation and another conservation, putting two conservations together do not give us a Z2 cross Z2 tilt symmetry. It's not this symmetry. And the reason is that there are some actual feature of this symmetry. So we better to say this V2 VZ2 some different combination, but not ordinary combination. And to see this actual feature, so we consider we're looking into these two symmetry more carefully. So one thing is we know that we consider so-called charge pair operator. We consider operator which create a pair of charge. To create a pair of the charge for the symmetry charge, we need a 2ZZ operator. Z changes left spin to right spin and create this Z2 charge. Okay, so there's a pair of Zi, Zj, create a pair of left spin, so that's a Z2 charge. And we call this charge pair operator as a patchy charge operator, because we view this as an open string operator with an empty box. Just two end is non-trivial, but the box is empty. We view this empty box open string operator. Then we also have a pair of dual symmetry charge. The pair of dual symmetry charge is easy to understand because to create a domain wall, just flip spin from up to down over the segment. So therefore, this one is really a string operator. We have a string of X dotted together, but the middle, they do not create anything. We say this operator creates a two-domain wall at its boundary. It's create two-dimensional boundary. So we view this spin flip operator as an operator create a pair of dual symmetry charge. Okay. And so again, this description is kind of strange. Say why you do that? Okay. It's kind of, the point is that you can see when you have the Z2 symmetry, is with a single Z operator would create a Z2 charge. And typically people study that. Okay. But however, we have trouble to create a single domain wall. We don't have operator creating single domain wall. Okay. So therefore, for dual symmetry, we only have an operator which create a pair of domain wall. Okay, to be fair to every symmetry, let's forbid this single Z operator. So we also say we only allow to create a pair of Z2 charge. Just like we only allow to create a pair of dual symmetry charge. Okay. Certainly there's a reason for that. Is that both these so both these charge pair operators actually act within the so-called symmetric subhilbert space. So when you have a symmetry, you can restrict yourself to the symmetric subhilbert space. When you do that, then both operator would act within this symmetric subhilbert space. So in some kind, they are kind of equal footing. So that's also hint something like the symmetry and dual symmetry became equivalent or equal footing within the symmetric subhilbert space. So that's also a very important concept. They're going to play a very important role later. Okay. So from here, let's look at this dual symmetry charge operator. This patch charge operator for the dual symmetry. It's just a spin flip along a segment. But then you say this one is nothing but the Z2 symmetry transformation for the original symmetry. So therefore, this Z2 tilt for the dual symmetry, the patch charge operator is a patch symmetry operator for the original symmetry. Yeah, from here it just looks like coincidence. But this may be a general feature. That is the symmetry and the dual symmetry have such a relation. The patch charge operator for the dual symmetry happen to be the patch symmetry operator for the symmetry. Means we do symmetry transformation only on the region, not in the whole space. And so again, this relate to another philosophy. That is actually patch symmetry operator is enough for us to describe symmetry. Usually when you say symmetry, we do symmetry transformation everywhere. But if you do symmetry transformation over the patch, this operator is enough for us to select local symmetric operator. Remember, only local symmetric operator are important. And once we have patch symmetry operator, we say the local symmetry operator are those operators which commute with this patch symmetry operator as long as my local operator is far away from the boundary. So therefore, this patch symmetry operator is as useful as my original symmetry operator. It turns out actually it's more useful. And so actually using the patch symmetry operator to look at the symmetry is actually more convenient. It's also a trick. It's play a kind of important role here. Yes.
So the endpoints are actually have some arbitrariness.
Yes, but however, yeah, this is crucial. The endpoint. Here I just do this. But when in general definition of patch symmetry operator, endpoint can be anything. You can add anything. But however, I try to not add a symmetry charge. So therefore, the ambiguity of endpoint is given by this local symmetry operator, which is defined by my patch symmetry operator. So then you may wonder, at the beginning I choose operator. How do I know whether? Okay, at the beginning you choose the operator called this patch symmetry operator. Then you have ambiguity at the point by this local symmetry operator. Then you can define the class of a patch symmetry operator, which is with the endpoint only differ by local symmetry operator, and that's enough. And so actually, you could have a different class of patch symmetry operator. Actually, if you put a charge on the boundary, you actually get a different patch symmetry operator, which later we'll talk about that. Yeah, and yeah, but at this stage, indeed, endpoint have ambiguity, but the ambiguity is given by local symmetric operator.
The local symmetric kind of depends on what the patch operator is at the endpoint. The patch operator itself can have endpoints. So
no, local symmetry do not depend on endpoint. Because local symmetry operator defined as operator commute with a patch far away from the boundary. So they do not depend on the boundary. And so then using that to define ambiguity of equivalent class of a patch symmetry operator. So it's a kind of consistent. But this kind of thing are very important because this is a way to using this local symmetric operator algebra to discover its symmetry. And there's some, but not today, but later we'll talk about that. That when you're given a algebra of a local symmetric operator, what is the symmetry? You know, it's not so easy to see when you have a lot of multiply together. What is symmetry? Actually, this is very similar to this Alex's way to do this scar. Yeah, the similar commutant. Yeah, basically it's a commutant can do that. And so the okay, so this is the point. Yeah, so we kind of see this. Okay. We use this, we demand this relation. That's the charge operator for dual symmetry is like a symmetry operator for the symmetry. So we kind of using this. Okay. And then if you follow this, then for the Z2 charge operator, which is a 2Z, then what is their symmetry? Then the trouble is that we have a 2Z operator, the bulk is empty. So there's no bulk. So it looks like we don't have a Z2 dual symmetry. We don't have their transformation. Their transformation trivial. Yeah. Okay. So yeah, so this is very confusing. Yeah, I think this is maybe one main problem with this dual symmetry. So for dual symmetry, we don't have transformation. So it's kind of strange situation. I just argue that we have a conservation law, but we have a transformation. We have a conservation law. We have a fusion ring, but we don't have a symmetry transformation. Actually, this can be turned around as another thing because the bulk is empty. If you insist this operator with empty bulk is a symmetry transformation of a dual symmetry, then you say any operator in Ising model is a symmetric because they all commute with empty bulk. So in some sense, this may be a good thing. That is that any local operator in the Ising model cannot break this Z2 dual symmetry. It's unbreakable symmetry. We can use from that way. But you can also say unbreakable symmetry means a trivial symmetry. But here is non-trivial in the sense that, you know, what I try to use this here. Yeah, the critical point do have a dimensional fluctuation. They control dynamics. So this conservation law should be non-trivial, should be something, you know. But when we think about the transformation, I have trouble with. Yeah, it's very confusing. But anyway, so let's insist on that. We say, yeah, we accept that. The Ising model, all the operating Ising model are symmetric. This dual symmetry cannot be broken. And this the transformation law of a dual symmetry is nothing. Don't do anything. The transformation law, it all sounds very strange. And but we still insist that the patch charge operator for symmetry is a patch symmetry operator for the dual symmetry. So indeed, we say this operator is a patch symmetry operator for the dual symmetry, which is bulk have nothing, do not do anything. So so there's a question though. We really want to see a non-trivial transformation of a dual Z2 symmetry, and this can be achieved actually using this duality mapping, the Ising model. Okay. So to make this Z2 dual symmetry more reasonable, one can do the dual mapping. This mapping is a standard, is a Kramer one-year transformation. Okay, and so it's a so here we have an Ising model. We have a ZZ and a spin coupling, spin live on the side, and we have X magnetic field. In a dual Ising model, our spin would live on the link. And we use this half integer to describe a link from I to I plus 1. Okay. The rule is that the Zi and Zi plus 1 became a spin Z in the dual spin on the link. And the single X became a X tilt on the dual spin on the two link. So then if you do this replacement, this kind of Ising model, this 2Z became a single Z, single X became 2X. And this transformation is exact because this X and ZZ operator have same algebra as this X tilt operator with a Z tilt operator. The algebra is identical. So this two model have same spectrum because the Hamiltonian is constructed by operator with the same algebra, so they have the same spectrum. Yeah. So that's what I call the duality mapping, almost like symmetry. Okay. But in the dual model, we see that well, we can have this we can have a Z operator. Z operator flip to X and do not flip a Z. So therefore, this product Z operator became a symmetry in the dual model. And this symmetry is what called the Z2 dual symmetry. Okay. And in the dual model, the original Z2 symmetry is a product of a bunch of Z. Product of a bunch of X. Yeah. With the product of a bunch of X, then the following when the Xi, Xj, Xi plus 1 multiply together, there's some overlap on this. They kind of cancel each other. So when you multiply a bunch of X together, you end up with operator with only X tilt and X tilt on the two ends of a string. The middle X tilt all cancel each other. So it's very similar. Original Z2 symmetry operator became this operator with empty bulk. So we have the same story. In the dual model, the original Z2 symmetry cannot be broken, no matter what kind of operator you add, what kind of local operator you add in the dual model. It's unbroken, unbreakable symmetry in the dual model. So now you can see that things get very symmetric. Okay. And so therefore this dual symmetry seems is okay. Yeah. And so to summarize that, in the transverse Ising model, we have a symmetry which is a string operator with non-empty bulk, and the dual symmetry is a string operator with empty bulk. But in the dual Ising model, the symmetry is a operator with empty bulk, but the dual symmetry is operator with non-empty bulk. So this became very symmetric. And then I want to emphasize that we will compare to these two models. I try to say that these two models are formed by operator with same algebra. So Hamiltonian should have same spectrum. And this is not correct. Actually, this is not correct. And these two Hamiltonian, when you put in the computer, they have different spectrum. However, what is important is that these two Hamiltonian indeed have the same spectrum, even for the space-dependent coupling and space-dependent magnetic field. They have a same identical spectrum in this symmetric sub-Hilbert space. So actually, this is what the duality mapping really means. Duality mapping do not mean the two Hamiltonian have the same spectrum; they are identical. Actually, only in limited sense they are identical. This limited sense is a symmetric sub-Hilbert space. But what is symmetric sub-Hilbert space? Because we are talking two symmetries, symmetry and dual symmetry. It's a weak symmetry. Actually, it doesn't matter. So actually, what we really mean is that in the Ising model, only symmetry acts non-trivially. So the symmetric sub-Hilbert space means the symmetric invariant under the original symmetry. In the duality model, only the dual symmetry act non-trivially. So symmetric subcarrier space is for the dual symmetry. But on the other hand, in the duality model, any state is a symmetric under the original symmetry because the original symmetry is identity operator. So any state is a symmetric subcarrier space. And similarly, in the Ising model, any state is a dual symmetry symmetric subcarrier space. So therefore, actually, this symmetric subcarrier space turns out to be the symmetric under both symmetry and the dual symmetry. So again, very symmetric. And so the claim is that under this symmetric subspace, this Ising model and the duality model have identical spectrum, and also they have identical correlation function for symmetric operator, not for, a symmetric operator would act outside here of space. That's no good. So for symmetric operator, they have identical correlation function. Okay. So this is really kind of like to say that if you imagine we have a situation where our experimental instrument cannot break symmetry, then we cannot tell whether we are studying Ising model or duality model. And their difference only became visible when you introduce the charge operator. The charged sector, the Hilbert space with a non-trivial charge, non-trivial symmetry transformation, they are different. And so the difference only in charge sector. So this led to the following thing, it's called the local equivalence. Because charge sector is like a global property. The symmetric sub-Hilbert space is kind of like a correlation function of a local symmetric operator, they kind of local property. And so in that sense, we say that the Ising model, dual Ising model are really equivalent, but really equivalent in the sense of local equivalence, means all the correlation function of a local symmetric operator are identical. So this is a kind of more careful way to look at the duality mapping. Before I kind of ignore the duality mapping by mistake. Oh, they map a local operator to the non-local operator is illegal. Anything can happen. So let's not think about that. Ignore that. And that's a big mistake. Otherwise, I can do this 10 years ago, maybe 20 years ago. If you take this duality mapping more seriously and understanding this more seriously, yeah. And so this is yeah. So that's one point. Okay. So this patch operator, now you can see why you introduce the patch operator. The patch operator actually is operator act again within the symmetric subcarrier space. So we look at everything within symmetric subcarrier space, then try to develop a theory within the symmetric subcarrier space. Again, this looks strange because that's also the beginning this puzzled us. That is, if you look at the symmetric subcarrier space, what is symmetry transformation? Their identity. They don't do anything. So it looks like when you look at the symmetric subcarrier space, you're missing any information about the symmetry. But on the other hand, we know that the critical behavior, all this dynamical property works well, even when you restrict to symmetric subcarrier space. These critical exponents are there. So it's really, actually, this really raises an interesting question. It's like all the symmetry constraints, symmetry property, symmetry restrict linear dynamics, all these phenomena are there in the symmetric subcarrier space. But our previous description of symmetry using global transformation somehow is not compatible with this picture. So even without, even when the global symmetry transformation act trivially, we should have a way to say, even within the symmetric subcarrier space, we can see the symmetry. The symmetry is there. So this is really a motivation to introduce a patch symmetry operator and a patch charge operator. They act within symmetric subcarrier space, but those operators can help us to extract information about symmetry. So this is a kind of shift the point of view of looking at the symmetry, not using global symmetry transformation. We look at symmetry within the symmetric subcarrier space and only using operators which are symmetric and symmetry, and then try to extract symmetry out of those. So that's basically like to detect symmetry using experimental instrument which do not break symmetry. How to do that? It's kind of like a way, this kind of way to look at the symmetry. Okay, so so with this kind of understanding of symmetry, now we can go beyond of a conservation law. It just mentioned that this Z2 symmetry and Z2 dual symmetry, it just reflects two conservation laws. Why we cannot combine them as usual, just Z2 cross Z2, that's it. Okay, it's really because, as you mentioned also in the last lecture, somehow this conservation law is a fusion ring. There's actual features. This actual feature beyond the conservation law is very much like actual feature we studied in topological order. So to see this actual feature, we can study this patch symmetry operator, a patch charge operator. You can see this W is a patch charge operator creating two Z2 charge. Okay, so let me go back to this patch charge operator. So W is just ZZ. It's a patch charge operator creating two symmetry charge. And this X string operator is a patch charge operator creating two dual symmetry charge. Okay. Now you can see that this two patch operator commute if they have this relation, if one contains another. But however, if the two ends straddle each other, then this only single Z are inside this patch. The X and Z single Z do not commute. There's a negative sign. So this feature really is here. That's if a boundary have this link, if a boundary of the two patch operator is a link, one is a patch symmetry, one is a patch, sorry, both are charge operator, one for the Z2 charge, another for the Z2 dual symmetry charge. Okay, then they anti-commute. So we will have this relation, they anti-commute. Okay. So then we view this operator algebra as a braiding. That is we view different order for operator algebra as different time order. Yeah, we view this vertical direction, time direction. So different order for operator is like a time order. And then these two ends can fuse together to form a loop. So almost like one charge braid another charge. It's like a braiding. Yeah. So we view this kind of operator algebra as a braiding for mutual statistics. Okay. So in some sense, we try to say that this actual feature is a mutual statistics for end of string. Something one actually mentioned. And here I also want to emphasize one thing that you can see a patch charge operator for symmetry and dual symmetry, they kind of neutral, you know, they are neutral by definition. And so there's no charge. They are charge neutral. There's no charge. But however, the patch charge operator have a feature. They are extended operator. They can be very long. When they are very long, somehow the end of a patch charge operator can be charged. So this is a fractalization. You know, if you only think of a local operator, we never have a charge. But when you glue many local operators together from an extended operator, you can have a patch charge operator. And then this extended operator review the fractalization. But here is not really fractalization. It's from neutral thing to get a charge. Originally, you have nothing. You don't have access for charged object. But by forming an extended operator from local operator, the end point or boundary for extended operator represent a charged object. And the charged object may have interesting properties. And here I want to say that this end of string, this charged object can have a non-trivial mutual statistics. And that is a new feature we try to say this new feature beyond the symmetry, beyond the conservation. And this point of view actually is very general. That is a local operator is nothing. But however, when the local operator form an extended operator, and the end of extended operator can have a charge, can be charged, can also be fractionalized. For example, you may have a local operator where we have a charge quantized integer. But then you may be able to construct a string operator. The end of string actually became fractionally charged. And here even further, you can say that the end of string maybe have fractional statistics. Although the local operator are bosonic, the end of string operator may be like a fermion. So those kind of things can happen. So this again is from this very, very simple example, we see something kind of unusual. That is from this innocent, very trivial local symmetry operator, we can discover some super selection sector with a fractional quantum number, fractional statistics, even fractional quantum dimension. All those kind of features can be recovered by constructing this extended operator. So later I will go into this further, but this is really the way to discover symmetry from local symmetric operator. How we discover symmetry, and that's also there's a super selection rule, a really selection rule for the end of a string. And somehow we can recover this selection rule enforced by symmetry, although we only work on the local symmetric operator. Okay, but anyway, for this particular case, because it's a non-trivial feature, then we say this 2Z2, Z2, Z2 tilde is a non-trivial. Yeah, so it's pretty simple. That is an ordinary, if a 2Z2 symmetry are independent, like Z2 times Z2, their charge would have a trivial mutual statistics, However, here, their charge have a non-trivial mutual statistics, so we say they are non-trivial. Yes.
There's a very similar algebra string operators in the 1D cluster state.
Yeah.
So, but there the global symmetry is actually Z2 cross Z2. Is that the same physics as this surface of the?
Yeah. I don't know when I may want to. Yeah, we should talk more. And it's following. There is a situation that we can have a 1+1D model with a Z2 cross Z2 symmetry, which are independent, really independent Z2. Okay. Then we can assign some large operators. We define a low-energy subspace. Then we find this patch Z2 patch symmetry transformation. Is the boundary is bad. The boundary do not act within the low-energy subspace. So you have to modify their boundary to make sure this patch Z2 symmetry and the patch Z2 dual symmetry both act within the subspace. And when they act within the low-energy subspace, they really like a Z2 dual Z2. But above this low-energy space, they are independent. They are both on-site operators. So basically, this symmetry is kind of like anomaly. I almost want to call them anomaly. You have Z2 cross Z2 with mixed anomaly. And so the example I just say that at the lattice model, you have a 2Z2 symmetry, no anomaly. But low-energy subspace, when the Z2 patch operator act within low-energy subspace, you have anomaly. So that's the emergence of anomalous Z2 cross Z2 symmetry from anomaly-free symmetry, actually. And this phenomenon is there. And actually, we even write the paper to say, this is a Z2 cross Z2 with mixed anomaly. Then you find it's a mistake. It's not Z2 with mixed anomaly. It's something similar to mixed anomaly, but they are not. So indeed, anomaly is an actual feature for Z2 cross Z2 symmetry. And this is also actual feature for Z2 cross Z2 symmetry. But the mixed anomaly and this feature are different feature. This feature are different. So yeah, so all these things become very interesting. So this actual feature can be pretty complicated. And what we call anomaly really refer to this actual feature beyond the conservation law. But how to systematically describe this actual feature in a unified fashion is really this motivation for categorical symmetry. This categorical symmetry really is a attempt to describe this in a unified, simple way. I think now we have too many anomalies. Things became very confusing. Yes.
Maybe I'm asking the same question, but in a different way. But is there anything wrong with doing this as a Z2 cross Z2 symmetry, but it's realized in a projective representation, and that's why it has bias?
Z2 cross Z2 is as a projective. I don't know. Yeah, but not obviously. Let me put it this way. For the Z2 cross Z2 with a projectation, we don't need to consider patch operator. We consider global symmetry transformation. It's just the algebra is not what we expected. And in that case, if you have two Z2 cross Z2 and their algebra is they don't commute, etc. So that's a Z2 cross Z2 with a projectively that's actually from Z4 symmetry. And this actual feature is not at the same level. It's not at the symmetry transformation level. If you do a global symmetry transformation, we don't see their difference. This difference, we see this difference at a patch operator point of view. We have to see their end of string, and the end of string has the actual feature. Yeah. So somehow this introducing a patch operator actually is very important, which allow us to see the actual feature of symmetry. Otherwise, it's hard to see. Yeah. Yeah. Yes.
So your the approach you're talking about here is like restricting to the symmetric subspace.
Yes.
Not allowing charge. The other way I can think of is to because the thing that's not quite included in the original Hilbert space is flux, right? That's the state that cannot be generated by the unitary operator on the original Hilbert space.
Yes, that's right.
So you could just say, okay, let's add flux.
That's right. Yeah, that's another way. So basically, yeah, one can also do that way. And so original Hilbert space, like the I think model on the ring, you have a charge neutral subspace and a charged subspace. Okay, you have two sectors. However, no matter what you do, you only have two domain wall. You never have a single domain wall. And the one way to make a single domain wall is to do the twist boundary condition. You say, I have another Hamiltonian, or just build another Hilbert space where I have twist boundary condition. So basically, traditionally in the symmetry, we say that two systems with two Hamiltonian. Okay. Then we forcefully put these two systems together. We consider the union of their Hilbert space. And then we get a fourth sector. Yeah. And so either twist boundary condition or no twist boundary condition with a charge or without charge. These two combinations give us a fourth sector. And then you can consider this fourth sector theory. That's also okay. Yeah, you should. And I think that's what give you equivalent theory. So here we choose the minimum one. This fourth sector theory give you the maximum one. And I don't know how. Yeah, certainly one can do that. And yeah, I don't know how to, when you're developing theory, what this point of view is what corresponds to what. It's not very clear. The reason I've considered this symmetric subhero space is because it's related to gauge theory. Actually, in the gauge theory, have a similar thing that in the gauge theory, the gauge charge always neutral. The total gauge charge always neutral. And so in some sense, the projection down to symmetric subhero space is almost like a gauging. Yeah, then the physics you see is very much like a gauge theory because you never allow single gauge charge. And then the situation you consider by introducing the twist boundary condition is like anti-gauge theory, but I don't know what's oh yeah, CFT can be like that, yes.
So kind of like matching the CFT on the boundary with the topological boundary with the gauge theory in the bulk.
Yes, yeah. That's totally right. Actually, later we'll go to there. So this so actually this is important, and yeah, the CFT. Actually, later we'll talk about the multi-partition function, multi-component partition function. Actually, this multi-component partition function is a one for each sector. That's exactly you need to have a full sector. So yeah, so, this play a very important role. Yeah. Yeah.
Maybe just a comment would be yeah. So one way to get the domain model to come in would be summing over all the boundary conditions that you use.
Yeah.
But the other way is just to like cut open your ring so you have endpoints.
Yes.
And if one of your endpoints is only a site without a dangling edge, acting your like flip spin on that site alone will excite only one domain model to the right of it.
Yeah, exactly.
So then you have one single domain model.
Yeah. So yeah, so this is what we missed here. That is we somehow only studied the icing model on the ring. And we should study it on with the open boundary condition. We should allow open boundary condition. And then even in that case, even when you reduce yourself to symmetric subcarrier space with the open boundary condition, things can be quite different. And so yeah, so that's so the whole thing here probably can be set up with open boundary condition. Maybe you don't need to do duality transformation to see the symmetry, dual symmetry together. That's the thing. And so here is very uncomfortable. Indeed, at the beginning we didn't have a patch symmetry operator. We're using duality transformation to argue, yeah, both symmetries are present. They should be treated equally. And Nati Steinberg asked the question, what is symmetry? It's nothing. You do not do anything. That's symmetry, etc. Can you see this symmetry explicitly, etc.? So really, because of his question, we introduced this patch symmetry operator, and so that to see symmetry explicitly even within the same icing model, we don't need to go to dual icing model. But yeah, but kind of thinking back, all these are really one can. Okay, let me put this way. If one look at this duality mapping more friendly, don't say they map local operator to non-local operator, they are bad mapping. Then maybe try to make sense of the duality mapping in a local sense. Then you basically arrive something like that, some theory like that. So the point is that it's very, very worthwhile to go back to literature. There's a lot of amazing duality mapping between different models, and all those duality mapping reveal something. From this point of view, you can see dual symmetry and all the combination. Yeah, maybe they can be kind of useful. Yeah, there's a lot of paper on duality mapping. Okay, so all we discussed is already. So far we discussed our discussion are really limited in one dimension. Okay, but somehow we have this. We view this order of operator as time direction, and we try to go to one higher dimension. So indeed, all these pictures have this holographic point of view. This is much easier to understand and capture this actual feature by go to one higher dimension. From operator algebra is a little bit harder, which we'll do later. But if you go to one higher dimension, it's pretty simple. For example, for this Z2 symmetry is icing model, we can consider the 2+1 dimensional Z2 gauge theory. And we have Z2 gauge theory, we know that we have this Z2 gauge charge. We also have this Z2 gauge flux, also is called E and M. And this F is a E and M bound state. Okay. And so therefore this So actually, this corresponds to this superconductor in 2+ dimension. You know, this E is like about quasar particle. This M is like a pi flux in superconductor, and F is a flux E bound state. So this Z2 gate theory is just like a superconductor. Okay, and so naturally we have this conservation law. Yeah, I should use this all times. Yeah, this EE has this mode2 conservation, and MM also have mode2 conservation. Yeah, but however in this in the 2+ dimensional Z2 gate theory, we can see their E and M have a mutual pi statistics. That is precisely this represent this kind of operator algebra. They capture this operator algebra through this kind of like a braiding. So here it's certainly not derivation. So it's a conjecture that all this actual feature actually is captured by this Z2 gate theory in one higher dimension. And this mutual statistic between E and M really capture this this operator algebra we talk about. Okay. And we also see that we recover this Z2 symmetry through conservation, through the fusion rule. So the conservation law is also there. And so this really led to this holographic picture that this categorical symmetry is a combined symmetry dual symmetry are precisely the topological order in one higher dimension of this Z2 gate theory in one higher dimension. Precisely means that even actual feature is there, is captured. For example, this E actually is a boson. So indeed, this patch operator, this end of a patch operator do behave like a boson. Okay. So all these features are there. And we can also see more. Because in the Z2 gate theory, we also have the bound state of a charge and a flux, which is a fermion. Okay. And the fermion also have a Z2 mode2 conservation. So it looks like we miss a symmetry. You know, there's another third mode2 conservation in the Ising model. Okay. And this symmetry is very weird. It's the end of a string should be fermion. Okay. And this actually relates to Xia's question. You know, two patch operator we considered, and this two patch operator. Now this generates a Z2 symmetry, this is a Z2 dual symmetry. But we can consider their combination. If you combine the two, that generates the combined Z2 and Z2 dual symmetry. And they should be fermionic symmetry. Okay. So there's another Z2 symmetry where the patch symmetry operator is this X, but with 2Z at the end. This 2Z at the end is like an illegal modification because Z is not local unitary, not local symmetric. It's charged. But when you do adding 2Z to the end, this symmetry actually became a Z2F symmetry. And this Z2F symmetry is kind of anomalous because the boundary have a Fermi statistics. But what do you mean by a patch operator, a string operator, their boundary have Fermi statistics? What do you mean by that? Well, at the moment, I don't know. No, I didn't describe. So later I will do that. So actually it's meaningful to talk about what the boundary of a patch operator, string operator is fermion or boson. It's a meaningful thing to do. But here we just use an analog. We say that yeah, this F is a bound state for E and M. You know, E and M, because although both E and M are boson, because E and M have a mutual pi statistics, their bound state is a fermion. So we have really weird symmetry that is have mode2 conservation, but however the end of a string operator is a fermion. So it's kind of like a self anomaly, you know, it's a self anomaly, but it's not. First, the Z2 symmetry in one dimension have a, let me see. Yeah, can be anomalous. I'm sorry. Yeah, the Z2 symmetry in one dimension can be anomalous. But however, the anomalous Z2 symmetry in one plus dimension indeed have a patch operator, have an end string. The end string is a semian, not the fermion. And so again, we encounter some funny situation. We have a Z2 symmetry, which looks like anomalous. But this actual feature is not anomalous. You know, anomalous symmetry is the end string is a semian. Here, end string is a fermion. So it's a, I don't know what to say. I can say there are two options. We can generalize the notion of anomaly. Okay. If you do that, maybe everything is anomalous. Okay. Or we can say that this kind of Z2F symmetry is a not anomaly-free, non-anomalous. It's something beyond anomalous, beyond anomaly symmetry. Okay, it's kind of weird thing. Yes.
What does anomaly mean in this context?
Okay, yeah, and I don't know. So anomaly, I think the definition, yeah, indeed, here I use a definition using the Bauer definition is is not gaugeable. It's approximate gauging, but that's still not quite right. Maybe this symmetry also cannot be gauged. Yeah. So I think here I'm using anomaly in the more narrow sense, means the boundary of SPT. Yeah, this is boundary SPT. So it's using boundary SPT to define anomaly, and this symmetry, this Z2F symmetry is not anomalous and non-anomaly free. And so again, I try to say that the anomaly now really became a, I don't know, should I say the bad feature? Something I don't want to mention. It's sometimes it's convenient, but when we can the more general situation, it can be confusing. So I'd rather call there some actual feature beyond the fusion ring. These actual features are described by these braidings, by some maybe F symbol. You know, here we don't see F symbol. We want to see the R symbol. This braiding. Maybe even F symbol may have something. You have remember we have two. We could have two fusion ring. We have same fusion ring, different F symbol. So F symbol, that feature is not really studied. You know, I don't know whether there's a good example for that. But those are actual feature, and it's a braiding statistic also actual feature. So those anomaly is a part of those actual feature, but only looking to that in a very strange way. It's much better to look at those actual feature beyond the fusion ring using F symbol, R symbol, those category language. Then all these actual feature of symmetry became very organized. So so maybe that's maybe the main point. So from this very simple model, if you really push hard, you can see the glimpse of those actual features and the direction. Yeah. So any other questions? Yeah. Okay. So I think maybe I would end here. So I think next Monday, there's Kansai who's visiting me. Will give this some lunch seminar about the one-dimensional non-invertible symmetry. So some symmetry is more non-trivial than what we studied today. We do study only just a Z2. Okay. Yeah. Another thing I want to say the following. Yeah. Maybe just as a motivation is that here we do the Z2. For Z2 symmetry, the dual symmetry is also a Z2 symmetry. But however, if this Z2 symmetry is non-abelian symmetry, the dual symmetry is not a non-abelian symmetry. It's a more than non-abelian symmetry. It's a non-invertible symmetry. So the dual of non-abelian symmetry is already a non-invertible symmetry. So this may be a simplest non-invertible symmetry. Yeah. And so therefore, when you have a symmetry breaking of a non-abelian group, the critical point would contain both non-abelian symmetry and the non-invertible symmetry. So it's a pretty so non-invertible symmetry is a pretty useful. I mean, it's pretty relevant, you know. Yeah. Okay, so I will stop here. Yeah.